Welcome to another deep dive. Today we'll be exploring something you probably remember from high school chemistry class, but something that's now on like the cutting edge of quantum technology. Yeah, we're going to be unpacking this essay, Cations, Schlüsselteilchen in der Quantentechnologie by Jorgo Schneepat.
Yeah.
It basically translates to Cations, key particles in quantum technology. So are you ready to dive into the quantum world of these positively charged ions?
Absolutely. I think it's fascinating how these, fundamental elements of chemistry are now playing such a crucial role in such advanced technology. It really highlights how interconnected scientific disciplines are.
Yeah, for sure. Okay, so for anyone who needs a quick refresher from chemistry class, what exactly is a cation?
Well, a cation is basically an atom that has lost one or more electrons.
Okay.
And since electrons carry a negative charge, losing them leaves the atom with a net positive charge, hence the term a cation.
Gotcha. So like if an atom loses some of its negative vibes, it becomes a positive cation.
Yeah, that's a good way to think about it.
I like that.
It all comes down to the balance between protons and electrons in an atom. And when that balance tips in favor of the protons, you get a cation.
Okay, so how do these tiny charged particles go from basic chemistry building blocks to, being the stars of the quantum show?
Well, that's where things get really interesting. Cations have these really unique properties that make them perfectly suited for quantum technology, especially in quantum computing.
Okay, tell me more.
All right, so in quantum computing, we use qubits instead of bits.
Right.
And unlike bits, which can only be 0 or 1, qubits can exist in both states simultaneously thanks to quantum mechanics. And guess what? Cations can act as those qubits.
Really?
Yeah.
So instead of the zeros and ones we're used to, we have these cations doing a kind of quantum dance, holding both possibilities at once.
Exactly. And this ability to be in multiple states simultaneously is what gives quantum computers their potential to solve problems that are impossible for classical computers.
Okay, so how do you actually use a cation as a qubit? I mean, it's not like you can just grab one with tweezers and stick it in a computer chip, right?
You're right. It's a bit more complicated than that. One way is to use what are called trapped ion quantum computers.
Okay.
In these systems, individual ions, which can be cations of elements like neurerbium or beryllium, are held in special electromagnetic traps.
So it's like a tiny invisible cage for these cations.
Exactly. And by using lasers and microwaves, researchers can manipulate these trapped ions. They control their quantum states and get them to perform computations.
That's wild. So the cations are literally the building blocks of these futuristic quantum computers.
They are. And it's not just quantum computing. Schneepat also highlights the role cations play in quantum cryptography, which is all about creating ultra-secure communication channels.
Oh, okay. So now we're talking about like secret agent stuff.
Yeah. Think of it this way. Right now, most of our secure communication relies on encryption algorithms that can be broken. Quantum cryptography, on the other hand, aims to create unbreakable encryption keys based on the laws of physics.
So it's like using the fundamental fabric of the universe to protect our secrets.
Exactly. And Cations are key players in this because of a phenomenon called entanglement.
Entanglement. Sounds like something out of Star Trek.
It kind of is. It's where two particles like cations become linked in such a way that they share the same fate, even when separated by large distances.
So it's like they have this invisible connection, kind of quantum telepathy.
You could say that. Now, imagine using this entanglement to create a secret key. If you try to eavesdrop on the communication, you inevitably disrupt the entanglement, and it sets off an alarm. This is what makes quantum cryptography so secure. Any attempt to snoop is instantly detected.
Wow, so Cations are not just quantum computing whizzes, they're also the ultimate secret keepers. What other surprises do they have in store for us?
Schneepat also touches on their role in precision measurements and materials science. For example, atomic clocks rely on the vibrations of specific cations. And in material science, researchers are exploring how cations can be used to design new materials with unique properties.
It's incredible how these tiny particles are impacting so many fields. It sounds like we've only just begun to tap into their potential.
Oh, absolutely. And that's what we'll dive into in the next part of this deep dive. We'll explore some of the future prospects of cations and how they might revolutionize everything from medicine and energy to even our understanding of the universe.
I can't wait. This is one deep dive I'm definitely not dozing off during.
Yeah.
Welcome back to our deep dive into cations and patience. It's pretty remarkable how these tiny particles from basic chemistry are now the stars of quantum technology.
It really is. And as Jorgo Schneppat highlights in his essay, there's still so much to explore when it comes to their potential.
Yeah, for sure. So Schneppat talks about using Cation-based quantum computers to optimize complex systems. What exactly does that mean?
Well, imagine trying to solve problems that have tons of variables and potential solutions, like way too many for a regular computer to handle.
Right.
Things like optimizing those big logistics networks, simulating the ups and downs of financial markets, or designing new materials at the molecular level.
So like trying to solve a giant Sudoku puzzle where the numbers are always changing.
Yeah, that's a great way to put it. Cation-based quantum computers could potentially handle those kinds of problems way more efficiently because of quantum phenomena like superposition and entanglement.
So they can explore multiple solutions at the same time instead of going through them one by one.
Exactly.
That's pretty amazing. And what about those precision measurement devices? We talked about atomic clocks before, but what other areas could Cations revolutionize when it comes to measurement?
Oh, tons of them. Schneppat points out the potential for developing sensors that are incredibly sensitive. Like, they could detect tiny changes in gravity, magnetic fields, or even temperature.
Wow.
And that could have a huge impact on fields like navigation, environmental monitoring, and even medical diagnostics.
So like a quantum sensor that could detect tiny tumors or track the progression of a disease?
Exactly. Or sensors that could be put into infrastructure to keep an eye on structural integrity and predict potential problems before they even happen.
That's incredible. It sounds like these sensors could give us a whole new level of understanding of the world around us.
Definitely. The sensitivity offered by Cation-based sensors could revolutionize our ability to observe and measure the world.
And we can't forget about secure communication. We talked about quantum cryptography before. Can you remind us what makes it so secure compared to what we use now?
Sure. So traditional encryption methods rely on mathematical algorithms that can be cracked with enough computing power.
Right.
Quantum cryptography uses the principles of quantum mechanics to create keys that can't be broken.
Huh.
It's like having a lock that can only be opened with a specific quantum key, and any attempt to pick the lock destroys the key itself.
Okay, and how do Cations fit into all of this?
Well, remember entanglement.
Right.
Where those two particles are linked and share the same fate, even when they're far apart, Cations can be entangled. And that entanglement can be used to create those unbreakable keys. If someone tries to eavesdrop on the communication, the entanglement's disrupted, and that sets off an alarm.
So it's like having an alarm system that goes off if anyone tries to look the message.
Exactly. That's why Schneppat sees Cation-based quantum cryptography as a potential game changer for secure communication.
So we've got quantum computers tackling complex problems, ultra-sensitive sensors probing the mysteries of the universe, and unbreakable communication networks. What's next?
Well, Schneppat suggests a lot of possibilities, including the development of new materials with totally customized properties.
Okay.
Like, imagine designing materials at the atomic level, where you're in control of their conductivity, their strength, or even how they interact with light.
So it's like being a quantum architect, building materials from scratch.
That's a great way to think about it.
This could lead to breakthroughs in fields like energy, transportation, and manufacturing. This is all incredibly promising. But Schneppat also mentions the challenges that need to be overcome. We've touched on the complexity of the technology and the difficulties of scaling things up. Are there any other hurdles researchers are facing?
One of the biggest is maintaining coherence in these quantum systems.
Okay.
Cations, while having those relatively long coherence times, are still sensitive to noise and interference from the surrounding environment.
It's like trying to build a sandcastle on a windy beach.
Yeah.
One gust and everything falls apart.
Yeah, good analogy. And maintaining that coherence is super important for these technologies to work reliably. Researchers are constantly working on new techniques to shield Cations from external influences, but it's an ongoing challenge for sure.
And then there's the issue of cost, right? Building these sophisticated systems can't be cheap.
True. The cost of developing and maintaining these technologies is still pretty high. But as research goes on and economies of scale come into play, those costs will likely decrease. It's similar to what we've seen with computers and smartphones. What was once super expensive and inaccessible eventually becomes affordable and commonplace.
It's exciting to think about the possibilities if these Cation-based technologies become more widely available. What kind of impact could they have on society as a whole?
That's a great question, and one that Schneppat really wants us to think about. we could potentially be talking about solving some of humanity's biggest challenges.
Wow.
Like developing new life-saving drugs and therapies, creating sustainable energy solutions, and maybe even unraveling the mysteries of the universe itself.
It sounds like Cations could be the key to unlocking a future we can only dream of right now. But before we get carried away with all these possibilities, let's take a step back and recap what we've learned so far. We've seen how incredibly versatile Cations are, from their role as qubits in quantum computing to their potential in cryptography, precision measurement, and even material science. We've also looked at the challenges that come with working with these tiny charged atoms, from keeping their quantum coherence to making these technologies affordable.
And as we'll see in the last part of our deep dive, researchers are actively working on these challenges and pushing the limits of Cation-based technologies.
I can't wait to hear more. Let's jump right into the final part and see what the future holds for these incredible little particles. All right, welcome back to our final part of our deep dive on Cations. We've learned a lot about them, from their early days in chemistry class to their big debut in the quantum world.
Yeah, it's pretty amazing how far they've come. And Schneepat really emphasizes in his essay that we're only just getting started with Cations. There's so much more we can do with them.
So where do we go from here? What are the next big steps?
Well, one major area that researchers are focusing on is improving the ion traps themselves. You know, those tiny cages that hold the Cations.
Yeah.
Those are super important for keeping the Cations isolated and protected so we can control their quantum states really precisely.
It's like a tiny high-tech fortress to protect those Cations from getting knocked around.
Exactly. Researchers are working on making these traps even more efficient, stable, and scalable. One exciting direction is miniaturization, making those traps smaller and more compact.
Oh, wow. So are we talking quantum computers that can fit in our pocket someday?
Yeah.
Like the way computers have gone from those huge room-sized machines to the smartphones we use now.
Yeah, it's definitely a possibility. Making things smaller would not only make these technologies more accessible, but it would open up a whole world of new applications. Just imagine quantum sensors so small that they can be put in medical implants to give doctors real-time information about a patient's health, or even sensors in bridges and buildings to monitor their structural integrity.
That's straight out of a sci-fi movie.
Yeah.
But miniaturization isn't the only thing that's happening, right? Schneepat also mentions improvements in vacuum technology. Why is a vacuum so important for working with Cations?
Well, it all goes back to maintaining that quantum coherence, that delicate balance in their state. Even the slightest disturbance can mess things up and cause errors.
So it's like trying to meditate in a busy room. You can't find peace with all those distractions.
Exactly. A vacuum creates a quiet space for the Cations, free from anything that could bump into them and interrupt that delicate dance they do.
So we're creating a Zen garden for Cations, huh?
Right. But then there's the challenge of actually controlling them. Manipulating these tiny particles with precision takes a lot of skill.
Yeah, I can imagine that.
And that's where another big research area comes in. Developing better control systems. They're exploring artificial intelligence and machine learning to really fine-tune the lasers and electromagnetic fields used to manipulate the Cations.
So we're talking about AI conducting an orchestra of Cations, making sure they're all in sync.
That's a good way to visualize it. This level of control is really key for scaling up these technologies. It would allow us to manipulate hundreds or even thousands of Cations simultaneously, making quantum computers more powerful and enabling more complex quantum simulations.
It sounds like there's a lot going on to push the limits of what we can do with these Cations. But Schneepat doesn't sugarcoat the challenges either, does he?
No, he's very upfront about the difficulties. Scaling up, minimizing errors, keeping costs down, those are all big hurdles.
But the potential payoff is pretty huge.
Yeah.
We're talking about possibly solving some of the biggest problems facing humanity. New medicines, sustainable energy, maybe even understanding the universe better.
And it's not just about those practical applications. The research itself is expanding our knowledge of quantum mechanics and giving us insights into the very nature of reality.
It's mind-blowing to think about how far we've come. From simple chemistry to the mind-bending world of quantum mechanics, all thanks to these little quantifications. It feels like we've discovered a whole new toolbox for building the future.
Absolutely. And thanks to the work of researchers like Yargo Schneepat, we're starting to see just how powerful that toolbox can be.
It's been quite a journey exploring the world of Cations with you, from quantum computing to cryptography, precision measurements, and even material science. These tiny particles are leading the way in a technological revolution. And Schneepat's essay really drives home the point that the future of Cation-based technology is incredibly exciting. It's a future where the mysteries of the quantum realm become solutions, innovations, and maybe even wonders.
And who knows what other amazing discoveries are waiting for us as we continue to explore the potential of these little particles.
So to everyone listening, keep your curiosity alive. Keep asking questions and pushing the boundaries. The quantum world is out there, ready to be explored. Maybe you'll be the one to make the next big breakthrough. Thanks for joining us on this deep dive into the world of Cations.